Welcome, I'm Jerry Paris, the founder and president of Paroscientific and Quartz Seismic Sensors. Here at our headquarters in Redmond, Washington, we develop and produce the world's greatest geophysical instrumentation. Our quartz crystal sensors played a key role in warning systems for natural disasters, such as earthquakes, tornadoes, volcanic eruptions, and tsunamis.
December 26, 2004. What began as an undersea earthquake in the Indian Ocean ended as the most deadly tsunami in recorded history, with nearly 240,000 lives lost.
This video includes a demonstration of our sensors, a tour of our manufacturing facilities, and a history of our quartz crystal technology. Here is a working demonstration of the atmospheric, oceanic, and seismic sensors used in disaster warning systems. Quartz crystal depth sensors, accelerometers, and barometers can measure tsunamis, earthquakes, and infrasound signals with a sensitivity of parts per billion. For example, the display shows a real-time plot of barometric pressure. The fluctuations with a magnitude of about a millionth of an atmosphere are called microbaroms, and they are generated by ocean waves hundreds of kilometers away from our facility. By lifting the barometer up and down by half a meter, I can spell UW for our academic colleagues across Lake Washington. The pressure change of about 5 pascals is about the same magnitude as the infrasound signals generated by distant events thousands of kilometers away. Examples include sonic booms, volcanic eruptions, earthquakes and tsunamis, snow avalanches, and severe weather. Here's a working demonstration of our quartz crystal depth sensors. The display is a real-time plot of the depth sensor output. The sensor is reading absolute barometric pressure plus the head of fluid in the pressure port tube. The engineering units are given in hectopascals that are about equal to centimeters of water level. I can change the pressure by changing the fluid head. These steps are about 1 centimeter. However, the proven sensitivity is microns at depths of thousands of meters. An earthquake in Japan generated a 1 millimeter micro tsunami that was measured across the Pacific in Monterey, California. The NOAA tsunami warning system was expanded from 6 to 39 stations after the Sumatra tsunami killed 240,000 people.
Earthquake off Japan was first detected by a dart buoy 25 minutes after the event. That allowed NOAA to generate inundation forecasts for Hawaii and the Pacific coast a full 6 hours before the tsunami actually struck.
The Tohoku tsunami was also measured with our quartz sensors at a disaster warning system south of Tokyo. 10 hours later, the tsunami was measured with our nano-resolution depth sensors offshore Monterey, California. Remote ocean bottom recorders measured a precursor event 2 days prior to the giant tsunami. Unfortunately, these measurements were not available until the recorders were recovered from the seafloor. One recorder got stuck and was not retrieved. Over 4 years later, it was found off the Washington coast. We brought it back home and it was in perfect working condition after surviving the earthquake, the tsunami, and the long journey back across the Pacific. A method of in situ calibration has been developed to eliminate drift. The measurement time span goes from a fraction of a second to gigasecond. We can now measure short-term events like earthquakes and tsunamis, daily events like earth tides, as well as slow slip events and long-term phenomena like secular strain and sea level changes. to generate a few earthquakes here with this little ball. On the seafloor off Monterey, California, we measure the seismic and pressure signals due to an earthquake in Chiapas, Mexico. Our quartz sensors were able to detect an underground nuclear test in North Korea over 9,000 kilometers away. The tiny acceleration signal was a few micro-Gs, and the pressure signal was a depth change equivalent to the thickness of a piece of paper. I can generate some tilts by moving this cup and changing the angle at which the accelerometer sits on this desk. In a borehole off the coast of Canada, microradians of tilt were generated by nearby gas venting. The sensitivity of our quartz tiltmeters is nanoradians. This is equivalent to a 1 millimeter deflection of a rod with a length equal to Earth's radius. The world's most accurate pressure and seismic sensors are produced at our headquarters in Redmond, Washington. Our manufacturing facilities include laser, resistance and pulse tick welders, induction brazers, mass spectrometer leak detectors, high vacuum bakeout equipment, specialized quartz crystal fabrication and test stations, primary standards, environmental chambers, automated test stands, and high-speed data acquisition and processing systems. The history of the development of our quartz crystal technology started almost 70 years ago. In the 1950s, there were no personal computers, no mobile phones, no self-driving cars, and no digital quartz watches. We watched rock and roll on our black and white televisions. I thought that more precise measurements could be made in a time domain, and that started my search for digital force sensors. These developments are recorded in my Museum of Mistakes and Occasional Good Ideas.